All right, so today, we're not just doing a math problem. We're actually going to solve a mystery. We're diving headfirst into a case that honestly looks completely impossible at first glance. Think of it like a mathematical cold case with one of the most intimidating suspects you've ever seen. So, let's get right into the case file.
So just imagine for a second, you're the detective, and this thing lands on your desk. I mean, where would you even begin?
And there it is, our mathematical monster. It's a 10th degree polynomial with 11 different terms. It's long, it's messy, and, trying to solve it with the usual methods, that would be an absolute nightmare.
This equation, this is the heart of our mystery. It's like the locked room, the secret code we have to crack. And trust me, by the end of this, you are going to see this thing in a completely new light.
So, what's our mission here? Well, our mission is to find the roots of this equation. Now, that's just a fancy way of saying we need to find the value, or maybe values, of x that make this entire giant expression equal to 0. Simple as that.
Every good detective knows that the first step is to look for clues. And in this particular case, the clues aren't even hidden. They're sitting right there in plain sight, disguised as all those numbers in front of the x terms. We call them coefficients, and believe me, they hold the secret.
Okay, so we've extracted the key pieces of evidence, all the coefficients. Now just look at them all laid out like this. You notice anything? There's this perfect symmetry. The numbers go up 10, 45, 120, 210, all the way to 252, and then they perfectly mirror themselves coming back down. That is our first major hint that something really special is going on here.
Now that we have our clues, we need a way to analyze them, right? We can't just stare at them. We need a tool, a special procedure from our source material that's going to help us process all this evidence and reveal the pattern that's hiding inside.
Now, the formula itself is based on a really cool idea called Newton's sums, which connects an equation's coefficients to its roots. But we can break down how we use it into a simple, repeatable process. In each step, we'll take a specific set of our coefficients, our clues, and we'll use them to calculate a new value, which we're just going to call s. And we're going to do this over and over to create a whole sequence of these s values.
All right, the investigation is officially underway. We're feeding our first batch of clues into the process to calculate our very first result, which we'll call S0. So what's it going to tell us?
And there it is. The result is 0. Okay, that's interesting. It's a nice clean number, but on its own, it doesn't really mean much, It could just be a coincidence. Any single clue can be misleading.
So we keep digging. We run the process again with the next set of clues to find our second value, sus1. Are we going to get some other random number? Or is this maybe the start of something more?
Whoa, 0 again. Now that is interesting. See, 1, 0 could be a fluke, but 2 in a row, in an investigation, this is the moment you start to suspect you're onto a real pattern.
So we came into this thinking we were up against some mathematical beast, but our investigation has just taken a really sharp turn. The evidence isn't confusing at all. It's shockingly consistent. There is a clear and frankly amazing pattern starting to emerge.
So we run the test for psi2, and the result? You guessed it, 0. The pattern holds.
How about for 3? 0 again. This is getting pretty wild.
And for 4? Yep, it's 0. At this point, the pattern is absolutely undeniable. And this just lays it all out. When we run the analysis for all 10 of our values from S0 all the way up to S9, we get the exact same result. Every single time. A perfect string of zeros. This isn't just a clue anymore. This is the key to the entire case.
All the evidence is pointing to one simple, elegant truth. The mystery is unraveling right before our eyes. It's time for the final reveal.
So what does this string of zeros actually mean for us? It means we can now take this incredible discovery and plug it back into our original mystery. It is time to see what our mathematical monster was really hiding underneath that big, scary, complex exterior.
And here it is, the big reveal. The source material shows that because all those s values we calculated were 0, our terrifying polynomial just collapses. It simplifies down to something so incredibly basic, it's almost funny. The monster was never a monster at all. It was just wearing a really, really elaborate costume. So because all those s values were 0, the math lets us simplify that entire beast of an equation, and the solution to this, well, it's beautifully simple, isn't it? X has to be equal to 1. But hold on a second. We started with a 10th degree polynomial.
Shouldn't there be 10 roots?
And that right there brings us to the final piece of the puzzle, this idea of multiplicity. See, a 10th degree polynomial has to have 10 roots, but, and this is the key, they don't all have to be different. Sometimes the same root just appears over and over and over again.
So, the case is officially solved. Our colossal polynomial has only one unique root, x equals 1. But it's a root that shows up 10 times. Our original equation, it was just a very clever disguise for x minus 1 to the 10th power all along. And really, that's what's so cool about this whole thing. It kind of makes you wonder, doesn't it? How many other problems out there that seem like absolute monsters on the outside are really just hiding a simple, elegant pattern, just waiting for the right detective to come along and crack the case?